All right. So I'm Alex. Nice to see you. And And as you can guess or deduce from the title, the talk is about combining the two topics I've been interested in and working on for the past couple of years. And also maybe to give you a glimpse of what the proof engineering work is a bit like working with proofs and formal verification. And the two topics in question are automated reasoning and total programming. So let's have a quick look at what those are. So automated reasoning is typically defined as a subfield of artificial intelligence. And the artificial intelligence itself, I would argue, is a bit like a buzzword, is a bit like teenage music or something. So in the 60s, that would be the Beatles and expert systems. In the 90s, that would be something like Backstreet Boys and recommendation engines. And nowadays, let's say Ariana Grande and large language models. So, but if you go back to the beginning, to the, let's say, 1950s, then artificial intelligence was broadly defined as essentially human-level activities that could be performed or people tried to apply computers to. And there were several tasks, like classical tasks that people tried to do under the scope of artificial intelligence, such as machine translation, nowadays Google Translate and other services like that, speech recognition, strategic board gameplay like chess, and particularly the task of theorem proving, so trying to automatically figure out proofs for mathematical theorems. So this is what we're going to focus on. And here, the methods that are used are the so-called symbolic AI methods. So the methods that manipulate some formal systems instead of trying to reason with statistics or probabilities. And typically, these symbolic methods are more precise. They give like these high guarantees, precise guarantees that mathematics needs. And over the years, over decades, in this field, there were quite a few tools implemented, such as SAT-SMT solvers, computer algebra systems, logic programming languages, and proof assistants. And if you look at this list, you can notice that it's roughly increasing in expressive power, but there's actually a fundamental struggle between this expressive power of a system and the degree to which it can be automated. So basically, the more powerful the system is, the more user input it requires, and at the end it becomes so interactive that it basically converges towards being a programming language. So here's a nice slide or diagram that illustrates this trade-off. So you cannot have basically a point in this space. So you have to choose in this line, and that's like if you're lucky. But essentially, here we'll use an interactive tool of a proof assistant, Agda, to build and verify some very simple model automated tools or cores of those. And the automated reason itself, so yes, that is a subfield of symbolic AI, now that you kind of know what that is, and which is focused on theorem proving using symbolic methods. And there are typically common features to these algorithms, these tools, and they typically operate on some kind of syntax representation with variables. So this is typically like a tree or a DAG or a graph. Like the more performant usually use graphs, like sharing different nodes, but nevertheless. So the important part, there's the syntax, there's some kind of variables inside it, and these tools, while they work, they synthesize some kind of proofs. Well, that's ideally what we want to do to prove theorems, but they can also synthesize some intermediate terms or refutations. So these are like counterproofs or proofs that something cannot be proven, and so on. And also one important feature that they typically work with functions in the mathematical sense, but these are like finite functions. These are finite maps. So basically like hash maps in programmer sense. So, and typically these maps, they map variables to terms or pieces of syntax or some kind of more complicated structures. So in this talk, we're only going to use first order syntax. So that means that the variables are kind of freely bound in the syntax. There are no way to add like binders, like lambdas, like to bind some of the variables inside the term itself. So it's just some term and some variables in it. And since we're going to do like a bit of formal verification, the important part when you're doing some reasoning about variables is called the context. And this is what logicians, type theorists, so people who work with this kind of stuff, denote by these capital Greek letters, like typically gamma, delta, and so on. And so the context is usually means a finite set of all the variables in the expression. So this is the context of the expression. And one kind of quirk is that this context is typically an upper bound. It's an over approximation. So for example, a term that consists of a single variable x can actually have a context x, y, z. So there might be some variables in the context which are not in the term. But they're still finite. So they're bounded from the top. And we'll use a special type for Agda. So for those who know a bit of Agda, this is a special quotient type to represent these finite sets of variables. So these finite sets basically are a bit like lists or like containers, but where the order and the multiplicity, and it doesn't matter. All that matters is the membership relation. So these contexts, they have usual set operators or predicates like this membership predicate, union of two sets, removal of a single variable, and set difference. So like the subtract one set from another. All right, so let's move on to total programming. So we're gonna essentially compute these maps from variables to something, and we want them to match mathematical functions as closely as possible in order to be able to formally reason about them. But what is the mathematical function? It's essentially a mapping from one set to another, such that set x, such that it assigns to each element of x exactly one element of y. So if we are already doing like pure functional programming, we're already pretty close to this definition, because we have, in the absence of side effects, we have this deterministic mapping of elements to elements. But how do we guarantee the parts about each and exactly once? So there are actually two problems that can arise here. So one is that not every x is assigned to y, and a canonical program to illustrate this is this Haskell head function that is undefined on the empty list, so it doesn't map anything to doesn't map the empty list to anything. Right, so it's a so-called partial function. And a second problem, which is much more insidious, is that the y is never produced, and this is canonically illustrated by this trivial loop program, which just spins forever, not doing any useful work. And these are not just like abstract mathematical concerns. There's been a somewhat recent study in 2022 that identified almost 1,000 security vulnerabilities that arise from non-terminating bugs. So some components of some systems failing to terminate and somehow allowing security breaches for this. So you can look in the study for the details. But also for the reasoning system, if you have a large reasoning system, like automated reasoning system, then typically these algorithms are just building blocks, parts of it. And if one part gets stuck, freezes, then the whole system doesn't give you an answer, which is like very annoying. So a way to combat this is to accept this paradigm called total functional or just total programming, in which you can only write by design programs which are covering all inputs and the terminating. So this first part about coverage is relatively trivial, though it often requires you to like be very precise about how you structure a program. That can be a good thing as well, at least for correctness. However, the second part involves recursion, which means it's very scary. So the way to start dealing with this is that we have in these total functional languages like Agda, we have this inbuilt notion of structural recursions. So put simply, these are programs which consume their inputs by syntactically decreasing pieces. So if you have like this trivial tree structure without any data, just like a shape of a tree, and you can compute the depth of this tree by recursively calling itself on the left and right nodes. So here L is like syntactically smaller than the input node LR. So the type checker sees that this is actually structurally decreasing and accepts this program. However, there are, and it's quite easy to find programs that doesn't fit the structural pattern, and the canonical such program is Euclid's GCD algorithm. So this is non-terminating. This cannot be seen as terminating. And the problem here essentially that in the recursive call, we swap the arguments. So we put the second one first, and in the place of the second one, we put the remainder of this modular operation. And so this, we know this converges. So this is an algorithm, like very old algorithm, but and essentially this works because for all m that are not zero, n modular m is smaller than m itself. So like 5 modular 3 is 2 smaller than 3. But this is not a structural expression. This is a computable expression, something that is derived by computation. So we need to be able not to just decrease in a predictable chunks, but like make arbitrary leaps when decreasing. And the pattern, or the like more powerful concept to do that, is called a well-founded recursion. So this is mathematical idea, but essentially it means that you have to introduce some kind of measure. So some type T that is equipped with this order relation, and it has to be a well-founded order relation. And put simply, this means that if you construct any sequence of these elements of type T, you cannot continue indefinitely to the left. Like at some point on the left, you run into a bound, like a lower bound. So a canonical type that is well-founded is just natural numbers with the usual less than relations. And this works because actually it's more structured. It's a linear order, a total linear order. So it always ends up with zero. So any such change just runs into a zero. But generally, these orders can be like more intricate. They can be branching. They can have multiple list elements for different chains. All matters that for each such chain, there is an element. It doesn't have to be unique or something. So in Agda, we can encode this pattern or this well-founded recursion by introducing a special type called box. So it's like a field with a single function. And essentially, this is a way, boxed A means that an A that you can only call and get a result out of if you provide an argument which is provably smaller than what it is indexed with. So you set like an upper bound on boxed A, and then when you call it, you have to prove that whatever you're calling it is smaller. And it turns out that if this order T that you index your type with is well-founded, that you actually can implement on a case-by-case basis, so like a type class, this fixed operation or fixed point operator. So a classical fixed point operator is just this, A to A implies A, but this can allow you to encode like non-terminating programs. And if you make it more complicated, so you index with this well-typed, well-founded type, and introduce this guard, this box, then all programs that are computed by this fixed point operator are terminating. So you can add a bit of syntactic sugar to make it less, more compact. So if you want to hide the measure, make it implicit, you use this for all quantifier. If you want to make it like explicit, participating in the computation, you make this a pi quantifier, but this is just basically sugar. And so here's how you would use it on, for example, the GCD function. So you define a type, so you index it on the first argument, and then the rest of the type is the second argument, such that it's smaller than the first one. And you have to write like a single iteration of the loop. So in this case, it's computationally relevant. You check the second argument. So this is like a special case operator that gives you the proof whether the y is actually zero or not. If it's not zero, you can do the recursive call. And now it is safe to do the recursive call because we required this less than proof in the type. This is the second argument, and we now have to fill in this second proof, and we fill it with this proof that the remainder is smaller than the modulo. So this is just some proof massaging starting from the y not equal zero. And we obtain this proof that we feed. And then we take the fixed point, and at the very last thing, what we have to do, because we fixed the order of the arguments, the first one has always to be greater. We have to decide which of the two is greater. And if the second is greater, we swap it and provide it with this proof to kickstart the computation. Yep. All right, so these are the domain and the technique. Let's now move on to the actual automated reasoning algorithms. And the first algorithm, which is kind of a tutorial, is a unification algorithm. So unification is very versatile. It's been called a Swiss Army knife operation or operator. And it's essentially a family of algorithms. Sometimes, like for more complex variants, these can actually not terminate by design, but like a simpler cases always terminate. And it works by essentially you're given it a pattern which has some holes or gaps, and these gaps are encoded by the variables in the syntax. And you match it against some data or some other pattern, and you try to fill in these gaps as precisely as possible, or fail if that's not possible. And there are many applications, and the classical one are logic programming, type inference engines in programming language. If you've seen the verse talk this morning, it's the verse language also heavily relies on unification. So the classical algorithm, like the simplest form of it, is called the MGU, most general unifier, like first order MGU. So this is described in classical Benjamin Peace's Types and Programming Languages book. And essentially it works like this. So you're given a pair of terms, or a list actually of like a working list of pairs of terms. And you want to find a substitution that unifies, makes them all equal. So like if you unify a symbol against itself, there's nothing to do. If you unify it against something else, that's a failure. If you unify a symbol against a variable, that's results in a substitution of that variable for that symbol. If you have some more complicated expression like x, a on the left, b, y on the right, it makes like this composite substitution. An important idea is that you cannot typically unify a variable with a term that has that variable itself, because that will lead to infinite computation. And as I said, you can have a list of these unification problems, like if x equals y and y equals a, then you should substitute them both for a. So the terms in this case are just binary trees. We have these, let's say, pair constructor, like a tuple constructor, and two leaf constructors. So one is the variable, and the other is this symbol, like a and b in the previous slide. And the symbols are basically just strings, and the variables are some abstract type. You can take them to be natural number strings. All that matters is you can compare them for equality. So the constraints are pair of terms. So this is how you would encode like x times b, a pair of x and b. And we have to introduce two notions of substitution. Basically, one is this internal notion of substitution. So that basically means you go through, given a variable and a term you're substituted for, you go through the term recursively. And when you hit the variable case, you compare the variables. If it's yes, then you return the term, and then reconstruct the term back. So you replace each occurrence of this variable with this term if it matches. And the external notion of substitution is just this finite map from a variable to term. So here's the entire code for the MGU. So this is without the termination guarantees. So you start with this list of constraints, or list of pair of terms. If it's empty, you're done. There's nothing to do. Otherwise, you peel off the head, the two terms. If they're equal, there's also nothing to do. You move to the next one. Otherwise, you start unifying them. And essentially here you have two main cases. So if on one side you have a variable, on the other side you have a term, then you have to do this occurrence check. So to check if the variable occurs in the term, so to avoid this infinite regress. If it is, then you fail. Otherwise, you call yourself recursively, but first you do internal substitution. You call unification recursively on itself. And when you're done, if you're successful, you insert this pair of variable term into the external substitution in the answer. And symmetrically on the other side. And a more insidious case is where you have two pairs. So here you deconstruct the pairs and add them back onto the constraint list. So as two new problems. So why does this terminate? You cannot just count constraints precisely because of this last case, is because you started with CS with just a pair, and now you've introduced two more. So you started like one constraint, and now you've added one more. So you've added one extra. So this doesn't terminate just based on that. So one option is to look at this context size, so count the variables in the term. So substitution does remove the variable because you systematically go through the term and remove all the variables. But in this pair case, the context stays the same because you just rearrange the terms. In the pair case, what decreases is the total size of the terms. So like for the tree, you can compute the total size. So for each pair is a degree higher. So since you deconstruct a pair, you collapse one level, and this decreases. So, but you have two recursive cases. You have one measure in one case, one measure in the other case. So they kind of conflict. And the solution is to just combine them. And from the order theory, we know that this is always possible. There is an idea of a lexicographic product. This basically means that you have two well-founded orders, like two natural numbers. And if you pair them, if you create a tuple out of them, then this can be smaller in two ways. Either the first components are smaller, respectively, or they are equal, and the second components are smaller. So anyway, you go in this tuple, like you decrease in some direction. So for unification, this means that either context decreases in the var case, or the var case stays the same in the product case, but the total term size decreases. So now we have to expand our input. The input now is a pair of context and a list of constraints. You have to actually also, an important thing, you have to add an invariant so that these terms, all the terms in the list of constraints are well formed. So all their variables are included in the context. And the unification type now looks like there's an input, it's well formed. And these two indices that we're indexing over, they're equal respectively to the size of the context and the total size of the terms. So if we take a fixed point of this, we're done. Here's, for example, what would be a recursive call for tuple. So previously it was just this. Now we just make it in a where clause. We call this recursively, but we have to also now provide the proof that the second component in the pair decreases. So this can be done. And proof that this new input is also well formed. So for the invariant, it means what you receive, you have to prove back at the recursive call. Okay, so if you're lost, or if you like followed up to this point and get lost or tired after this, it's not a big deal, because basically by now I've kind of showed you all the main ideas, the context, the variables, the lexicographic product, the need for totality. But if you want to see like a more complicated theorem proving algorithm or automated reasoning algorithm, so let's move on. So a more complicated one is called the SAT problem, or the Boolean satisfaction problem. And this is a classical task from this area of constant satisfaction tasks. So this basically, you're given some problem with some constraints, like think of like Sudoku. So you have like partially filled in, and you have to obey these constraints to solve the problem completely. So in the case of the SAT problem, you're given a Boolean formula with these variables again. And you have to find an assignment of these variables that makes the whole formula true, or fail if there's no such assignment. So this is somewhat similar to unification, but we restrict the range of variables. So we map the variables not to arbitrary terms, but only to these ground true or false terms. And we add an extra semantical constraint that whatever we do, the whole formula has to evaluate to true under Boolean laws. So there are, of course, different problems that have different solutions. So, for example, there are problems which are tautologies. That means no matter what you assign to the variables, it stays true. So, trivially, it's just the true itself is always true because there's nothing to assign. But also, for example, if you know that P and Q are true, then one of them must be true. So, this sounds logical, but can be encoded like this, and this is true no matter what. Like more complicated logical laws, like Peirce's law, is also a tautology. Then there are formulas which are satisfiable. That means there are some assignments that make it true, some assignments that make it false. For example, this formula can be falsified if you assign P and Q to true and R to false. Then this simplifies to true implies false, which is false. And there are formulas that are unsatisfiable no matter what. The simplest one is basically this contradiction. P and not P cannot be true at the same time. So the most common approach to solve such a task is backtracking search. So that basically means you just go through the problem and systematically try to assign a value to a variable. And if you run into false, if your formula evaluates to false, you backtrack and change one of the previous choices. However, that's 2 to the power of n operations. So that's exponential complexity. As you can imagine, not very fast in bigger cases. Can we do better? In the worst case, no. And this was proven in 1971. The problem is incomplete. You have to do, like, in the worst case, the full search. However, you can apply some heuristics to try to cut down on your search as much as possible. And the algorithm that does that, and it forms the core of most of SAT solvers, is called the Davis-Putnam-Loveland, or DPLL for short. These are just the names of the creators. So it still performs this backtracking search procedure, but it used these heuristics to try to minimize guessing as much as possible. And there are 3 such heuristics that it uses. Unit propagation, pure literal rule, and literal selection. One important note that these algorithms, such as DPLL, they typically assume that the formula you give it is not just some arbitrary formula, it's been normalized. It has this conjunctive normal form. That means it's converted into a form that is a conjunction on the outside of disjunctions. So these are called clauses. So it's A or not B, and not C or D or E, and so it's like a bit like a matrix representation, sort of. And we know from logic, because we have these Boolean reasoning principles like excluded middle, De Morgan rule, that we always can convert a formula into this form. This is not true for constructive logic or intuitionistic one. So, for example, true becomes just an empty CNF, false becomes a single empty clause, P and Q becomes a pair of P and Q singleton clauses, and so on and so forth. So now that we have these, how do we encode this CNF representation? So unlike in unification, where we have this well-formedness invariant that we had to track through the computation, now we push the well-formedness constraint into the literals themselves. So a literal can be a positive, negative. It holds a variable, basically like a string or something, and the proof that it is in the context that it's indexed with. So you can project out the variable and the polarity, like if it is positive or negative out of a literal. Then the clauses indexed by context is just a list of literals, and the CNF is a list of clauses. So a CNF is a list of literals. And you can collapse it one level with a flatten or concat operation to get like a list of all literals in your problem. Okay, so the heuristics the DPLL uses, first one is basically the most important one. It's called the unit propagation or one literal rule. It basically it's basing on this observation that you have if in your CNF one of the conjunctions is a clause that has only one literal, that must be true, because if it's false, then the whole thing becomes immediately false. So it's basically it searches through your CNF, tries to find a clause which is a singleton. And if it does, it returns such a literal. And then the unit propagation procedure goes through the CNF. It removes all the clauses that have these literal in the positive occurrence, because it has to be true, and the disjunction with true is automatically true. And it filters out the negative occurrences. And what's important, so if you combine this, you get like a pair of a literal and a CNF. And if you look at the type, this is the most important part. That means you were given a context gamma, and now your context has this literal that you found removed from it, so it is decreased by one literal. The other one is called pure literal or affirmative negative rule. It's more complicated, but basically the idea is to delete every literal that occurs only positively or only negatively, so purely, because also these can be assigned straight away. And here I just show you the type. The implementation is quite big, but basically you're given a CNF and you're returning a list of literals that occur purely, such that if you project out their variables, they intersect with the context gamma, and the context is decreased by all of them. So all of them are subtracted from the context. And this is needed to know that at least one of them is in the context, so it decreases by at least one literal now. And if this is not possible, if the procedure fails, then this is an either. Then it returns a proof that for every literal, it's included in the literals of your problem, both positively and negatively. So these two heuristics, basically what they try to do is they try to cut out as many literals as possible before trying to make a guess, but at some point you have to make a guess. And this is where backtracking is happening, where the exponential behavior is happening, so you want to minimize that. So the split-in rule is basically just a way to choose a literal to guess on. And this is one heuristic you could use, like a simple one is called just the positive-negative rule. It basically just means you count how many times the literal is included in your problem, like both positively and negatively, and you choose the one that is occurring the most frequent one. And you need to basically also provide the proof that there are some literals in your CNF, so at least some positive ones, because after the previous heuristic, you know that every literal is included both positively and negatively. So if there is a literal, it is included positively, and so this is guaranteed to return some literal. So if you put all of this together, so you can say like a type of answer is a map of from variables to booleans. We just use like internal Agda booleans. And so one pass of this algorithm does the following. So first it checks if the CNF is empty. If it is, then it is, as we've seen, the trivial true formula. We're done. There's nothing to do. Otherwise, if it has an empty clause, that means it simplifies into false, then we fail. Otherwise, we start applying our heuristics. First, we apply the one literal rule. If we succeed, then we call ourselves recursively on the smaller problem. And once we return, we insert the literal into the answer. If we fail, we try the second one. Again, if we get back the list, we call ourselves recursively and insert all of them into the answer. And the most complicated part is if both of these fails, that means we have to do the guess. So we have to choose the literal according to this heuristic splitting. And then we have to we try first to add the literal as a single choice to the problem. But if we do that, then on the next recursive call, the unit propagation is going to kick in immediately. So we just do it right away, like inline this recursive thing. If that fails, then we try again. So this is like a choice with the negation of it. So one of these has to succeed. Well, maybe if it succeeds, then so this returns like either this or that. And then you deconstruct that either and insert the corresponding literal into the answer. So this is basically the core of the entire DPLL algorithm. Why does this terminate? As you can probably guess by now, this is because the context always decreases. So all the heuristics, they decrease it by at least one. And this is indicated in the type. And this is actually a simpler termination metric than unification. So the algorithm itself is more complicated, but the termination is much simpler because basically it's expressed recursively. So in this case, we don't need this lexicographic argument. We just need a single number. So the type for these terminating DPLL would be like given a context, which is indexed, and the type is indexed on some number. That number has to be the size of the context, and then it's basically just the type for the problem. Okay, so that was the recursive DPLL formulation, but the catch is, or like the sad part is that that is not very efficient. And the real world SAT solvers, like Z3, if you heard of it, they're actually using a different form of this algorithm, which is iterative. So the problem here is we're doing the backtracking search, but this backtracking information is stored on the system stack. So this recursive call is not in the tail position. It's these map operation that comes after it. So whenever we do a recursive call, we push things onto the stack, and the language runtime has to take care of it. So the way to make it more efficient with some more engineering, but like a core idea is to make it tail recursive and or iterative. And the key idea to do that is to make this stack, this call stack in the algorithm, a first-class object. And in the implementations of SAT solvers, this is usually called a trail structure. So a trail structure is basically a stack of these literals that we are guessing, but we also add a flag. And with the flag, we indicate if the literal was actually guessed, which serves as this backtracking point, or it was deduced, so it follows from our previous guesses. So yes, a trail indexed by gamma is just a list of literals paired with their flags. And you can project the literals out of the trail, and you can convert the trail to the answer, to this map of variables to booleans, by simply folding through the trail and updating the map with the variable and polarity of each literal. So we still need the heuristics, but actually we can simplify them a bit. We can get rid of the pure literal rule, and for efficiency, we perform this unit propagation in batches. So we don't do it one literal at a time, but we do it as much as possible until we can. So basically, we filter out the initial problem such that it does not have the trail does not contain any negations of the literals in it. And then we compute the new units. So we find all the unit clauses that are there. And then if there are none, then we're done. We just return the new CNF and the trail. Otherwise, we call ourselves, but we add all the new units, literals with the flag of being deduced. So we just know that they have to be set to their corresponding polarity. And we call ourselves recursively. This filter operation might unearth some more pure literals, so we repeat this until we cannot anymore. So now, basically, the algorithm itself basically has only two choices. So first we call this batch unit propagation procedure. We get back a new simplified CNF and a new trail. If this new simplified CNF has an empty clause, that means we've reached false inconsistency. We have to backtrack on our previous guess. And backtracking on a guess now, because we have the stack as a first-class object, is basically going, starting from the head of the stack, discarding all deduced variables, because that means our choice was wrong. We need to find the most recent guess. We return this literal. And if this succeeds, if this fails, then it means there were no guesses. The formula is just unsatisfiable. If there was a guess, then we have to invert it, so make it negated. And now it has to be deduced. So now basically we know that our choice was wrong. The only other possibility is that the negation is true, and this is deduced. This is not something that we have to backtrack on again. We've exhausted the possibility. The other possibility is that this new CNF does not have a falsity, and we just exhausted all pure literals, and now we have to do the actual guess. So in this case, we select one of the unassigned literals in the CNF, and if there are no unassigned ones, then basically we're done. We found our answer. We convert the trail to the answer, and we're good. Otherwise, we do the recursive call, but we choose the literal again according to a splitting rule, and we flag it as guessed. So it's kind of simpler, but not really. So why does any of these things terminate? So for this batch unit propagation, the measure is actually the count of the literals that are still not on the trail. We multiply it by 2 because each literal can be positive or negative. So we say that so for the length of the trail, what is decreasing is the literals that we have not yet tried. However, this only works when the trail is unique, because otherwise this thing can go like into negatives. And this is like one invariant that we have to maintain through the algorithm. Why does the main loop terminate? So for the guess case, this measure also works, like these unused trail literals, because we're adding new guess literals, so we're exhausting the unused ones. But what about the backtracking case? Because we backtracked, we basically removed a chunk of the trail, and we've removed a bunch of literals. So this measure increases, the trail shrinks and the measure increases. So we're kind of reminded of this situation from unification. We have basically two kinds of recursive calls. One needs one measure, the other needs another one. So this kind of hints to us that we need to use the lexicographic product again. And for the second case, for the guessing case, we can use the unused literals measure. But what is the first one? So, like, we have to really think conceptually about this. Intuitively, what we are exhausting when backtracking is the size of the search tree. So if you write down the whole problem as like one big tree, so for each node that you're guessing, you have two choices, if it's true or false. So you systematically make these choices. At some point, you run into inconsistency, you flip back, like mark this as non-viable and do the other branch. And so basically, you're kind of traversing this search tree left to right in this kind of left to right order. But the search tree, we cannot use it itself as the measure, because we compute the search tree on the algorithm. This like creates a circularity. We need to somehow approximate this tree, like find some kind of proxy to use as a measure. So if you look closely at the tree itself, we notice that basically what we're doing, once we've discarded the possibility, for example, of B being true, this discarded literal like B positive B sticks. We never remove it from the upper levels. So what sticks around are these discarded literals. However, we cannot just track all the discarded levels in a single level, because when we backtrack, we reset our choices. So these discarded literals, they accumulate one level up, so they kind of slowly propagate up, can be removed from the lower levels, but they stay up on the upper levels. So basically what we need to do is we collapse the tree like vertically into a vector. So these borders of these vectors are these guessed literals, and between them we maintain these a set of discarded literals. So then there's we apply the measure of the literals. We count literals which are not still yet discarded, and since such a vector, we can make it's the size of the context, the size of total variables in the task. It cannot get bigger than that, so it's like a static measure. And we can basically think, and since it's a static vector of a known size, we can think of it as n-ary lexicographic product. So it's a product of A times B times C. So, and then basically once we backtrack, we increase, what happens is we increase the vector one level up. So that means that the n-ary corresponding components of the vector can decrease. So this becomes like a very big lexicographic product. And then the full measure is then this vector and the product of it with the unused variables in the trace. So I'm not going to repeat this completely, but it's, you can imagine a non-trivial measure. And for all of this to work, we still need some invariants. So one of the invariants that was needed for the unit propagation to work, that was variable for polarity, should not repeat. The trail should be unique. But for the DPLL, it turns out there's a second invariant that is needed. If a guessed variable is the trail, that negation also doesn't appear it. So then the guessed variables are unique, not only up to polarity, but up to their name. And this vector stack, like this auxiliary or ghost structure that we need for termination, also actually needs an invariant. It's a bit complex, that it basically says that if you look at some level into the vector, then the negation, if it appears in that section of the level of the vector, its negations should appear somewhere in the trail after dropping the corresponding n literals. So basically, when you are composing all of this together, you have to prove that all of these invariants are preserved, which is a bit of work, but luckily for us, all of this works out. All of these invariants are preserved in the algorithm. And the full termination type looks like this. So we index by a vector, which is size of our context times number. We're given a trail, this stack of rejected variables, their corresponding invariants, and the first component is this map of sizes like unused literal sizes, and the second one is just unused trail sizes. Okay, so what have we kind of learned from all of this experience? So basically writing out these proofs, be it correctness proofs or termination proofs, kind of forces you to understand what your algorithm preserves, what is changing in it, like how it works. And if you have one non-trivial control flow, then this can become like very complicated. But once you determine the invariance, you have much more freedom into changing your data structures, the representational algorithm. You know, like what has to be true for the algorithm to still work. And more generally, automated reasoning is not magic. It's basically mathematically just operating with syntax, with finite sets, with order relations, and like there's quite a theory called order theory. And maybe last but not least, the order theory itself can be thought of as a cut-down version of category theory, but that is perhaps a story for another time. So there's quite a few references, links you can find in the repo, but most importantly, I want to single out this book from 2009. So this has all these algorithms described into it. If you're interested, it's a very, very good book. And here are some contacts and the repo for the talk where you can find these slides. And that's it.